Good day, everyone. I am Jersen Villanueva, and my co-presenter is Christopher Eleazar. We are undergraduate civil engineering students from the LaSalle University taking CALENG3 differential equations. There are multiple applications of differential equations, such as population growth and decay, radioactive material decay, falling object, Newton's law of cooling, and beam and columns deflection. In civil engineering, beams and columns are the major structural component which are subjected to axial load. They also play an important role in making structure more rigid and stable. In deciding beams and columns, different factors are considered and analyzed carefully, wherein in some instances, differential equations are used. Beams and columns deflection is the bending of the component due to applied loads. The bending of a beam or columns occurs when the compressive load of the component reaches its critical value. The main causes of beam and columns deflection are wind load, shear load, uniformly distributed loads, and point loads. Failure to compute the deflection properly can result in serious deformation and damages, as components will tilt and collide.
In relation to that, the calculation of bending moments require engineers to have profound knowledge on differential equations, as this is the basis for derivations. In order to demonstrate this, let's tackle our sample problem about bending moments. Suppose we have a water tank supported by a beam column. Now, this water tank experiences forces such as the axial load big letter W and the lateral distributed load small letter w. How do we calculate the lateral deflection of this beam? To start things off, the differential equation that describes the lateral deflection is given by this equation. But it isn't as simple as just plugging in the numbers. No, we need to extract this general solution for this. The first step is to solve the complementary solution to the homogeneous dE, so we isolate the left side of the equation and equate it to 0. Converting this to the auxiliary equation, we have d to the 4th power plus alpha squared d squared. We then factor d squared out to find the roots. We know that the roots are 0, 0, so that's 2 times, and then the imaginary positive negative alpha I. Now, the general solution for this will be a combination of real and repeated roots, and then a complex conjugate root. Therefore, our solution will be equal to C1 plus C2x, that is for the repeated 0, and then plus C3 cosine alpha x plus C4 sine alpha x. Now that is out of the way, next is the particular solution, which is quite tricky. In this video, we will be using the d operator method, but there are other methods that can work as well. We start from this equation. We isolate the y variable first and then factor the alpha squared d squared. Next, we expand this expression resulting to, and this is very important, 1 minus, we copy the middle second term as is, which is d squared over alpha squared, plus we square it, d to the 4th over alpha squared. We then distribute w from the expanded expression, so like the second derivative of w with respect to x is 0, and then fourth derivative of w with respect to x is still 0. Then that's 1 minus 0 plus 0, or simply 1. We simplify this using this substitution, and so we are left with this, wx squared over 2w. Now that we have the general solution, we need to find the constants. For that, we have boundary conditions which can be used by substituting this general solution to these arguments. I'll just summarize this part as all we need is just some simple derivatives and substitution. But I'll provide a link in the description if you need this part. In the end, we resulted with this equation. And this equation describes how much the beam column will bend given the flexural rigidity EI, the length L, and some other properties of the beam like the alpha. The main takeaway from this is that differential calculus is used in engineering prominently, especially in civil engineering if you want to study theory of structures and the like. Knowledge in differential equation, although only found in derivations, is one of the foundations of a skilled civil engineer. If you want to read more on this kind of application, check out Wei Cho Xie, Differential Equations for Engineers. That's all, and thank you for staying till the end.